right, number 88. Homework.
This site from me to have the wording of the question, right?
The wording is where? Yeah, let's take a look at that. Let's see, go ahead, Mike. Okay, that would be one of the more challenging problems.
Yeah.
Okay, a researcher dissolved 1.32 or 1.382 grams of impure copper. Right, so we would stop there and just kind of, we have a piece of impure copper, 1.382 grams. Okay, this is copper plus impurities. And so it's a mixture. So if we need the percent composition of this mixture, that is, let's say it's 99% copper, 1% impurities, then we could just use that to take us into the stoichiometry map because we need copper initially. And so a lot of problems would be like that. And so we reacted with nitric acid to produce a solution of copper 2 nitrate. So the solution went through a series of steps in which copper 2 nitrate was changed. Right. So when we do this in nitric acid, then what we have to say is that these impurities are going to be inert. That is, the impurities are not going to contain copper, for one, so they shouldn't be copper impurities. Although, I don't know, is this copper metal? Copper, yeah. And so we'll just call that inert. And so what we're going to do is we're going to convert all the copper. We're going to assume this. We assume all copper metal is converted to copper 2 nitrate. So what this tells me is I don't even have to come up with an equation. This is a time saver because here I can just say that all the copper I had, if I had 1 gram originally, then all 1 gram of that copper ends up in copper 2 nitrate. And so it's just a time saver. Otherwise, I'll have to write out the equation. You know, writing out the equation for copper is not too bad if you use the chart method. And single replacement doesn't work with. All right. Then the solution went through a series of steps in which copper 2 nitrate was changed to copper 2 hydroxide. And so there are a series of steps. And so all the copper from here ends up here. And so we have to assume 100% yield. This looks like a metathesis reaction. How do you do it? We probably can do it in one step. You know, to convert copper 2 nitrate to copper 2 hydroxide is probably pretty easy. What would you add? Just add hydroxide. If you add hydroxide, copper ions like hydroxide ions. So you could add lithium hydroxide, potassium hydroxide, sodium hydroxide, whatever you want. And so I would think we can do this in one step. But we don't need to know what they added. They just are telling us that all the copper 2 ends up there. And then to a solution of copper 2 chloride. Oops, then to copper 2 oxide. So we convert the hydroxide into oxide. This is probably an acid-base reaction, Lewis acid-base, in which they remove water, an H2 and an O. maybe even H2 and an O will get copper 2 oxide. And then to a solution of copper 2 chloride. So you can take this oxide and react it in hydrochloric acid, you'll probably form this, copper 2 chloride. And so we have to assume that we're getting 100% yield. If we're losing some of this, then what they're getting at is not going to work. This was treated with an excess of soluble phosphate, precipitating all the copper in the original sample as pure copper 3 phosphate. And so they're going to mix this with phosphate. Well, copper ions like phosphate ions. So we form Cu3PO42 salt. That's what we got there. The precipitate was dried and weighed. Its mass was 2.637 grams. Find the percentage by mass of copper in the original sample. So what we do is we'll end up with 2.637 grams of this stuff. And however many grams of copper we have in here must be the same as the grams of copper that were in the original. So let's say I started off with 1 gram of copper in the original. All 1 gram of copper in the original should end up here, assuming we didn't lose any, which could have happened, but we're just going to assume it didn't.
So then the middle part?
Yeah, what we do is we essentially ignore the middle part and then just say this. The mole ratio is going to be 1 mole of copper phosphate requires how many moles of copper? You go all the way back to the beginning, and we're doing copper metal, and so for every 1 mole of this, we have 3 moles of copper, and so that's going to give us 3 moles of copper. And so 3 moles of copper are required to produce 1 mole of copper phosphate. So we're going to skip all the middle stuff and just go to the end. There are 2 ways we could do this. One way is we could just figure out how many grams of copper is in this compound, and then, well, all whatever grams those are came from the original copper sample over there. Or 2, we'll just do it stoichiometrically, where we'll go from the product here to the original reactant there. So let's do that. They want us to find the percentage by mass of copper in the original sample. And so we could break this up into 2 parts. Normally in Chem 1A I'd do this in 1 step, but let's break it up into 2. And so this is stoichiometry. I just do 2.637 grams of copper phosphate, and then I'm going to convert it to moles of copper phosphate. And from moles of copper phosphate, then I'm going to convert it to moles of copper metal. And then from moles of copper metal, I'll convert it to grams of copper metal. Okay, once I have the grams of copper metal, then I can figure out the percent copper in this original. So the percent copper by mass is equal to the grams of copper over the grams of sample times 100%. So the grams of sample comes from that stoichiometry calculation there. So we'll just plug that in here. And then the grams of sample, they give it to us. It's 1.382 grams of sample. And then we multiply by 100%. Does that answer it pretty much?
Yeah.
I have a question.
Uh-huh.
I don't understand how you got the mole ratio.
The mole ratio is just based on the formula here. For every one of these, how many coppers did I need to react? And so for every one of these, I need 3 coppers to react. And so in order to get 3 of these here, then I would have to do this. I'd have to multiply 3 here, 3 here, 3 here, 3 here, 3 here to get 1 of those. And so I didn't balance it, the situation. Once I balance it, then it would work out that way. But it's not a complete equation. this only works because we're only forming one product. Let's say I was burning charcoal. If I burned 1 gram of charcoal, which is carbon solid, and that was converted into CO2, how many grams of carbon do I have in my CO2? And so if I burn all 1 gram of charcoal, how many grams of just carbon are in CO2? One gram. Atoms are neither created nor destroyed. And so if I burn all 1 gram, all that 1 gram has to end up in CO2. So this is going to give me 1 gram of just carbon in CO2. That works if it's 100% yield, right? Works if it's 100% yield. It also works if there are not multiple products. If there are multiple products, then forget it. It doesn't work. Because let's say I burn my charcoal and I get carbon monoxide, carbon dioxide, and a little bit of soot. Well, soot is unreactive, so I'll just go carbon monoxide and carbon dioxide. Now, if I burn 1 gram of carbon, I don't know how much of that ends up in carbon monoxide and how much ends up in carbon dioxide. So this is a 2 unknown. 2 unknown, I'm going to need some more information. Excuse me. And so what they're saying in this problem is, it's not. What we have is, what do they call it? Like when you can trace things. Traceable, you know. Like legal. We do the same thing. We trace things. You know, one way to trace this is to isotopically label it. And so if we isotopically label, put radioactive carbon here, then we can figure out how much, whatever, you know, this type of stuff. But not necessarily in this case. And so we can just trace the path that copper takes all the way to the product. Each of these reactions we should be able to do. I mean, this first reaction is redox. Use the chart method. Products would be copper 2 nitrate, nitrogen monoxide, and water. The second reaction is metathesis. Copper likes hydroxide more than it likes nitrate, so it's going to precipitate out there. This next reaction is Lewis acid base, though. This is where we're going to get rid of an H2 and an O, form CuO. This one, I don't necessarily, but if you had copper 2 hydroxide and you were to heat it up, this is solid, and you were to heat it up, this triangle means heat, then one of the potential products would be copper oxide solid plus water. That seems reasonable. Then here we can take copper 2 oxide, react it with acid, HCl, and form copper 2 chloride and water. And then we'll just precipitate out with phosphate. So all those steps we can figure out. But we don't have to figure them out. We don't have to figure out any of those steps as long as we know that all the original copper ends up in the final product. So I could have ignored everything and went straight to the copper 2 phosphate at the end. Okay, any other questions? Does that answer? That's useful for multi-step reactions. There are a lot of multi-step reactions. You can just skip all the intermediate steps and just look at the stoichiometry and the beginning. But it means we have to balance all the intermediate steps to make sure everything's balanced. Okay, if there are no more questions on this, let's go back to what we were talking about yesterday. so, Bohr theory. Bohr theory, remember this whole idea of orbit? The whole idea of orbits turned out to be wrong. How did they determine it's wrong? Well, how they determined it's wrong is this. Bohr theory orbits, this works only for one electron species. More than one electron, it fails. Well, most things have more than one electron. And therefore, Bohr theory was abandoned. And so if the Bohr theory didn't quite work out, what do we need more of? To come up with a new hypothesis, we might need some additional observations. And so there were a couple of additional observations which I talked about. What were the additional observations we had? One additional observation was the wave-particle duality of light and matter. The wave-particle duality of light and matter. And so what this says is that light has, when we think about light, what is light? We think of waves. Waves moving at the speed of light, oscillating electric fields. That's energy. Light. This is energy. Does energy have mass? Like, have you ever tried to weigh a calorie? You could weigh things that would give you a calorie or calories, but can you weigh just the calorie itself? Can you weigh the light that's coming off the light bulb? No. And so normally we don't think of light as having any mass. We don't think of light as being a particle in the normal sense, but light has particle-like qualities. And so a particle of light is called a photon. And photons come in different sizes or energies. And so if we're looking at a gamma ray photon, this is a high energy photon. Whereas if we're looking at a radio wave photon, this is a low energy photon. And so this comes up, this brings up the comparison. What would you rather run into? Would you rather run into 100 pounds of feathers, or would you rather run into 100 pounds of lead brick? Some people go, oh, it's 100 pounds. 100 pounds is 100 pounds, so it doesn't matter, it's 100 pounds, whether it's feathers or lead brick. But is it really? No, it's not at all. Yes, it is 100 pounds, and both are 100 pounds, but what's different? What is different between 100 pounds? Well, feathers consist of feathers. But lead bricks consist of bricks, and those bricks are heavy and dense, and it's going to hurt. Well, that's it. This is like your lead brick. This is like your feathers. And so we could have the same amount. So for example, what would you rather be hit with? 100 watts? A watt. You know what a watt is? A watt is 1 joule per second. 1 joule's worth of energy per second. And so would you rather be hit with 100 watts of gamma radiation, or would you rather be hit with 100 watts of radio waves? Yeah, radio, but some people might say, hey, it's 100 watts. 100 watts is 100 watts. Is it? Well, it is 100 watts. It's the same energy. What's different? The photons are different. The photons are different. And so this is why if you do any kind of, like in the pre-digital camera days, they had film, and for the film they had dark rooms. They had dark rooms because they didn't want to expose the film to light. It would pretty much ruin the film. And so if you have a dark room, how can you see? Well, do you know how you can see in a dark room? They had red light bulbs. Why red light? Because red light would be the lowest energy visible light. And so with red light, you're going to minimize the exposure of the film and minimize the damage to the film. Would you want to use blue light? No, because then you're going to ruin the film. And so the difference is, well, you could have a 100 watt blue light bulb or a 100 watt red light bulb. A 100 watt red light bulb will have lots of little photons. A 100 watt blue light bulb would have a fewer number of big photons. The big photons are going to cause the damage. And so this is the particle nature of light. The particle nature of light. Think in terms of that. Okay, it turns out that matter has wave properties. Matter has wave properties. This isn't noticeable. This is not noticeable until it becomes confined to a very small space. And so it turns out that all matter, for example, the electron has wave properties. So imagine you're an electron fish swimming in the ocean. If you're an electron fish swimming in the ocean, can you swim at any speed you want? Pretty much? Well, not any speed, but any speed within your capability. Yeah, you can go from 0 to whatever speed you want, right? If you're a fish in an ocean. And so an electron, like in the sun, the sun, there are electrons in the sun, and the electrons in the sun pretty much can go any speed they want. If they want to go 25.1 miles an hour, then no problem. They can go 25.1 miles an hour. It's not a problem. Or any speed between. But what happens if what happens to a fish if you take it out of the ocean and put it into a smaller and smaller and smaller aquarium? So let's take a whale and put it into a SeaWorld. Can that whale swim any speed it wants? No, pretty soon it's confined into a small space. If it's confined into a small space, then there are other constraints that you have to worry about, right? And so it turns out that when we take an electron, we don't notice this. We don't notice this for like a regular light bulb. In a regular light bulb, there's this tungsten filament. Tungsten is W, so we'll call it solid. And in metals, are the electrons loosely held or are the electrons tightly held in metal? They're loosely held. The electrons are free. They're pretty much free to go wherever they want. And this is why metals conduct electricity. And so this electron is like a small fish in a big pond. A small fish in a big pond, it can move any speed it wants. It can move slow, red, a little bit faster, orange, a little bit faster, yellow, right? It can move whatever speed it wants. So pretty soon, since it can move any of those speeds, we're going to get the whole rainbow of colors. We're going to get what we call a continuous spectrum from this. Because of this. When we look at the wave properties of an electron, the waves are so, this is like a fish wagging. It's, okay, this is the speed of this electron. Now this fish wants to go a little bit faster, so it's going to add one more half stroke, of propulsion in there. If it adds one more half stroke of propulsion, then let's say, in order for this electron to travel from here to here, it had to do this like a billion times, right? Back and forth to make it from one end to the other. A billion times. So it wants to move a little bit faster. It's going to have to do 1,000,000,001. Is there much of a difference in energy from 1,000,000,000 to 1,000,000,001? Is it going to be moving all that much faster? Would you even notice it? Probably couldn't even tell. It looks like it's moving the same speed, but it's just moving a tiny bit faster. Right? And then the next one would be 1,000,000,002. We'll get 1,000,000,002 wags of the whatever tail fin there. And it turns out that, okay, basically when we have a big volume like this, the electron can pretty much have it can't. It turns out that energy is quantized here because we can have 1,000,000,000, we can have 1,000,000,001, 1,000,000,002, but the difference in energy is so small, it appears to be continuous. And so this is 299,999,000. And so it appears continuous. These are energies. And so this is increasing energy here. Energies appear continuous. And indeed, the difference in energies is so small, it is essentially continuous. And so this is like an electron in a big pond. An electron in a big pond, it could go slow, it could go fast. So we make it a little bit faster, it absorbs a little bit of energy. Make it a little bit faster, it absorbs a little more. What happens though if we start making the pond smaller and smaller, and pretty soon it's like a little fish bowl? When we have a little fish bowl, then it makes a difference. And so we're going to put that electron in a very tiny, tiny, tiny volume called the atom. And so this is tungsten metal, which is a crystal, a piece of wire. But if we went to a tungsten atom, then all of a sudden things change because now that electron is no longer confined to, this will be the nucleus here, that electron is no longer confined to a huge volume like that. The electron is confined to a tiny, tiny volume. And now how many wags of the tail does it take to get from here to there? How many wags of the tail does it take to get from here to there? Half a wag. And this is the way it works. And so to go from here to here, we'll just put in one half wag. It can't do part of and so it has to do like a half. And then, or we could get one full. Back and forth. So, one full. What's the difference in speed between one and one full one? Is it negligible? Will you even be able to tell the difference? No, you'd be thinking it's probably moving twice as fast here, right? And so, what's the next one that we can get? The next one would be up, then down. Let's see, did I get it right? Up, and then back. And so what it looks like is rather than continuous, like this, where it looks much more discontinuous like this because there's a big jump in energy here. And then again, there's going to be another big jump in energy here. And so we call these wavelengths, half wavelengths. And so here we can fit 1/2 a wavelength in here. Here we can fit 2 1/2 wavelengths. Here we can fit 3 1/2 wavelengths. This would be 1. But could we fit like 1/4 of a wavelength? We couldn't really fit 1/4 of a wavelength in here. No. Otherwise it won't be able to turn around and go back. Does that make sense? A little bit? And so here there's more significant difference in energies. This will be noticeable jump in energy. Jump in energy. Over here, this is a negligible jump in energy. And so what we have here is energy's always been quantized. You know, just for large objects would be like, you know, big ocean. It wasn't noticeable. You know, it wasn't noticeable. It's just when you get into very, very small things like the atom, then it's noticeable. And so these wavelengths become noticeable for very small systems like this. And so that's why a lot of people will say, well, quantum mechanics deals with the very small. Have you heard that? Very small. That's because that's when you notice the impact of wavelength. Not for very large. And so now, if the electron's swimming in an atom, we have to worry about how many of these half wavelengths we get in here. Because what happens is, if it's not an integral number of half wavelengths, we have something like this. This has to do with wave properties. If you take a wave like this and another wave like this, when they meet, they can do two things. One, they can cancel each other out. That is, if they're offset, then the peak of one wave will match up with the trough of another wave. So if a peak matches with the trough, then the waves cancel each other out. That's called destructive interference. Or they can constructively interfere. That is, a peak of one wave will match a peak of another wave. And so if we have an electron like this, the peaks have to match and the troughs have to match, otherwise it's going to cancel out and it's going to be forbidden. And so we have to make sure that there are integral number of half wavelengths in there, otherwise it's forbidden. And so the next jump would be, well, this is 3 half wavelengths, we'll need, the next jump would be 4. Over here, this one is 1 billion half wavelengths, the next jump will be 1,000,000,001 half wavelengths. Well, the difference in energy between 1 billion and 1,000,001 is negligible. So it's nothing. So this is this is one observation. What was the other one?
Heisenberg's uncertainty.
Heisenberg's uncertainty principle. With Heisenberg's uncertainty principle, we have to visualize the electron totally in a different way. You know, with the Bohr model, we visualize the electron like this. In the Bohr model, we have the nucleus here, and we have an electron orbiting around the nucleus. And then this could be the lowest energy orbit, and this would be a higher energy orbit, and a higher energy orbit. So we have a bunch of orbits. Right? But with the Heisenberg uncertainty principle, what was the Heisenberg uncertainty principle? Heisenberg uncertainty principle said that, what did I write down on the board? Well, basically it boils down to this for us. The Heisenberg uncertainty principle says if we pinpoint energy, the energy of the electron, and we want to know the energy of the electron, for sure. If we pinpoint the energy of the electron, then we cannot pinpoint the position of the electron with certainty. Then we cannot pinpoint the energy, not energy, position, sorry, position of the electron with certainty. If there's uncertainty, then we speak in terms of probability. Probability rather than absolutes. And so what we're interested in is we're interested in the energy, and therefore the position. It doesn't mean we know nothing about the position. It just means that there's going to be a certain probability in the position of the electron. And so this is the Heisenberg uncertainty principle. So what we can do is, this would be the bird nest analogy. The bird nest analogy goes like this. Bird nest analogy. Okay, let's say there's a nest here for the bird. And let's say you pinpoint the bird. I'm going to pinpoint the bird's position right here. The bird is here. And I see the bird there. Can you tell me how much energy that bird has today? Any way to tell? No. And so if we pinpoint the position, then we don't really know what's going on with its energy. Well, that's not very helpful. We want to know the energy. And so what we're going to do is we're going to look at the energy. We're going to pinpoint the energy. So let's say the bird, it's a low energy day. If it's a low energy day for the bird, then we don't know exactly where its position is. But in one instant, the bird might be here. Okay. Can you tell where it's going to be in the next instant of time? Do you know what direction it's flying? That kind of stuff? No. But what we'll do is we'll just say, okay, there we see it. Here we see it. Here we see it. Here we see it. We know that since it's lower in energy, it's not going to deviate that far from the nest. And so here, and pretty soon, we're going to just follow and watch this bird over a long period of time. We watch this bird over a long period of time, and then we see that mostly it stays close to the nest, which is here. Once in a while, it might be further away from the nest. Once in a while. But most of the time, it's pretty close to the nest. And therefore, we don't exactly pinpoint its position, but what we can do is we can do this. We can look at the dots and then go, okay, if we had 100 dots here, we'll put 95 of them in a certain boundary here, like this. And so what we call this is this. We'll say that there's a 95% probability that the bird will be in this boundary, and a 5% probability that the bird will be outside that boundary. And so 95%, and then outside we'll have 5%. That's it. What if the bird had higher energy? If the bird had higher energy, do you think this would describe? No, if the bird had higher energy, then we would expect it to deviate even or travel even further from the nest. And so if the bird had higher energy, this 95% boundary should grow, expand. It just has higher energy. Well, this is what we're saying here. We don't, if the electron's orbiting around the nucleus like this, we can pinpoint it, its position, and we know its energy because it's at this orbit. But in quantum mechanics, what we have to do is we have to think, because of the Heisenberg uncertainty principle, we have to think that, well, we can't pinpoint it, but it's somewhere around here. And we can't really predict which direction it's going or anything like that. And so it might be here one instant in time, but 5 minutes later, I don't know. We just know within 95% probability it should be contained within this volume. And a 5% probability it's outside that volume. Now, if it had higher energy, it'd look like this. And so let's just look at the boundary. Here we have our low energy bird. Here we're going to have a higher energy bird. And so the boundary is going to be bigger. Here we're going to have an even higher energy bird. And so the boundary is even higher. So lower, higher, higher. This is what we call an orbital. Orbital. In fact, these two, number 2, these two plus Bohr original idea led to the modern day theory, which is quantum mechanics. This is modern day theory of chemistry. Quantum mechanics. Quantum mechanics deals with these things called orbitals. Orbitals, what we have is we have a description of the electron. The electron energy and the electron's position within the atom. The position is going to be based on the probability. The energy is pinpoint. Heisenberg actually was less strict than this. Heisenberg was either you know the energy and don't know the position, or you know the position and don't know the energy, or you make some compromise for both. Well, we're going to pick a side, and we pick the side of energy. We want to know the energy, and therefore the position is going to be off. And that's what we call an orbital. And an orbital is the allowed energy, or I shouldn't say state, energy and position. I should say allowed state for an electron. And so from quantum mechanics, we can figure out what's allowed and what's forbidden for the electron. How do we figure out what's allowed and what's forbidden? We go through the theory. So the theory is too much. And so we're going to skip the math. Actually, before skipping the math, I better talk about the equation. The equation for quantum mechanics, which I'll abbreviate QM, quantum mechanics, is the Schrödinger equation. The Schrödinger equation is going to tell us the energy and the position of the allowed states for the electron. For example, the math is not so easy, but for example, the H atom. How many allowed states are there for an electron in a hydrogen atom? For an H atom, we can use the Schrödinger equation to determine that there are going to be an infinite number of allowed states. There are an infinite number of allowed states. If there's an infinite number of allowed states, does that mean that there are no forbidden states? No, you know what it turns out? There are also an infinite number of forbidden states. So there's an infinite number of allowed states and an infinite number of forbidden states. Do you want to solve the Schrodinger equation for each and every allowed state? Is it even possible to do it? Really? No. What we want to do is we want to look for patterns. You know, when we have a lot of, I mean, that's a lot, we're going to look for patterns. And the patterns that we're going to look for are mathematical patterns. And it turns out, yeah, there are mathematical patterns because, you know, mathematically, a forbidden state is going to violate the Schrodinger equation. An allowed state is a solution to the Schrodinger equation. The allowed states are called orbitals. The forbidden states are just called forbidden states. And so, what are the orbitals? There's an infinite number of orbitals. That's a lot of orbitals. Obviously, you aren't going to be expected to memorize all infinite orbitals for the hydrogen atom, unless you want to try. But it's easy. It's easy. It's actually easy because it follows a simple pattern. And so what we're going to do is we're going to look for the mathematical patterns. The mathematical patterns. These patterns lead to restrictions. For the allowed states. Each answer, each orbital depends on 3 variables. And so each orbital, which is an allowed state, depends on 3 variables. And so the answer turns out to be a mathematical equation itself. And you have mathematical restrictions on these variables. And so the orbital is going to be defined by these 3 variables, n, l, m. In order to solve the Schrodinger equation, n has to be an integer, like 1, 2, 3, all the way to infinity. And so these are allowed. What about 1.5? Is that allowed? 1.5 is forbidden. This would not result in a solution to the Schrodinger equation. And so n has to be a non-zero integer in order for it to work in the Schrodinger equation. And so this is one of the mathematical patterns or mathematical restrictions that we see. And so rather than listing up all infinite orbitals, we're just going to list off the restrictions on these. The next variable is L, well n, and 1.5 is forbidden. N is called the principal quantum number. The principal quantum number tells us pretty much the energy. N equals 1 would be the first energy level, or the lowest energy. 2 would be the next higher energy, next step up, etc. L is going to take on all values from 0, 1, 2, 3, up to a max of n minus 1. So for example, if n is equal to 1, then n minus 1 is 0, and And so we're only allowed one L value, which would be 0. If n is equal to 2, then we're going to have two L values, 0 and 1. If n is equal to 3, we'll have three L values, 0, 1, and 2. These are allowed. Everything else is forbidden. We give letter designations to this. We call 0 S, 1 P, 2 D, 3 F, etc. It would just go alphabetical on that. Right. And then one more mathematical variable, that would be, well, actually, did I tell what L is? L is, I don't think you need to know the name. Okay, what L does is L tells us the shape of the probability distribution. The probability distribution is like this nest thing. Well, when we draw all these dots, each dot represents finding the bird once. So this is called a probability distribution, or AKA the electron cloud. And so if I'm looking for the electron's going to be somewhere in this cloud. And then I might have a boundary drawn here. So it'll be somewhere in this cloud with 95% probability, 5% probability it's outside this boundary. And we have different shapes of these. That one happens to be spherical over there. L is called the angular momentum quantum number, but we don't need to know that. M is called the magnetic quantum number, but we don't need to know that either. M is going to take on values depending on the L. And so what we're going to say for M is for each L value, we get M values that are going to range. So we'll take all M values from minus L, dot, 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 to 0, dot, 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 to plus L. And so it depends on what the L value is. If L is equal to 0, then we're going from minus 0 to plus 0, so there's only one 0. If L is equal to 1, then we're going to go from minus 1 to 0 to plus 1. So there are three different M values, minus 1, 0, and plus 1. If L is equal to 2, then we're going to go minus 2, minus 1, 0, plus 1, plus 2. So there are 5 M values, etc. So let's build out the what we're going to call the orbital energy level diagram. The orbital energy level diagram, like I said before, we want to pinpoint the energies. And then we're going to recognize that each of those energies is going to have some kind of electron cloud or probability distribution associated with it. In other words, it's some kind of shape associated with it, describes it. And so if energy goes up like this, then the lowest energy is going to be n equals 1. If n equals 1, then that's the lowest energy, the ground floor there. If n equals 1, what L value can I have? Then L is going to equal, I'll write that up here. L will equal 0. Is L equal 1 allowed or forbidden? If I have n equals 1, is L equals 1 allowed or forbidden? Forbidden. Schrodinger equation. So if n equals 1, L equals 0, then what is my M value? It's going to go from minus 0 to 0, which is just one value. Minus 0 and 0 is the same thing, it's just 0. And so the first allowed state we write like this. We write in the NLM designation. N1, L0, M0. This is called the 100 orbital. 100 orbital. The 100 orbital. That's allowed. Well, 100 is a mouthful. And so what some people do is they'll just shorten this and they'll call it the 1s orbital. What does the 1s orbital look like? That's it on the bottom. Do you see it? 1s orbital. It's a 95% probability. What's next? Well, that's it. When n equals 1, that's all we get. What about when n equals 2? What do we get? When n equals 2, then L can equal, can L equal 0? Yes. L equals 0, so we're going to get 2, 0. What can M equal? M can also equal 0, so we're going to get the 2, 0, 0 orbital. The 2, 0, 0 orbital is also called the 2s orbital. But that's not all, because if n equals 2, L can also equal 1. And so let's write that over here. I'm going to separate this into columns. So this is the L equals 1 column here. Now let's go to L equals 1. It turns out that when L equals 1, it's going to be slightly higher in energy than L equals 0. And so what we're going to get here is something like this. If we do L equals 1, then we have 2 for N, 1 for L. What is M equal to? Well, M is going to be minus 1, 0, and plus 1. This is going to go from minus all the... So M equals minus 1. If M is equal to minus 1, then we get the 2, 1, minus 1 orbital. But that's not the only one that's allowed. M can also be 0. It's going to take on all values. And so this is going to give me a 2, 1, 0 orbital. And then finally, M can equal plus 1, which is going to give me a 2, 1, plus 1 orbital. These three orbitals are called the 2p orbitals. The 2p orbitals. And there are 3 of them. 3 of them. Now, how does that differ? How does a 2p orbital differ from a 2s orbital? Well, 2s orbital is this ball here. A 2p orbital looks like this. We have 3 of them. It's this kind of this dumbbell shape or figure 8 shape. Do you see it? This is one orbital here, and so it has a weird probability distribution. And so this is the 2, 1, minus 1. This would be the 2, 1, 0, and the 2, 1, plus 1. And the only difference is the orientation. They're all exactly the same, except this one's oriented on the x, this one's oriented on the y, and this one's oriented on the z. So sometimes what we do is we'll do this. Sometimes we'll call it the 2px, 2py, and 2pz. 2px, 2py, 2pz. Although I got to double check the numbers here. 2px, 2py, 2pz. And so this is what I mean. L tells us the shape. What does M tell us? M tells us the number. M tells us number and orientation. Number in the sense that each unique M value is 1 orbital. And so we get 3 unique M values, which means we have 3 orbitals. And so we end up with 3 p orbitals, the 2px, the 2py, and the Z. And that's the shape, and this would be the energy here. Or we're gonna stop and take a break here, and then we'll continue after break.